So next we have a student talk. So this is Assaf Har-Noy from Roey Amir's lab in chemistry.
Hear me? Okay. Last year, I remember that I attended a conference in Malahide, which is near Dublin. And I don't remember much because they don't have coffee breaks, they have Guinness breaks. But I do remember that the first or second speaker, she introduced herself and showed the university she comes from. And she showed a picture of a river. And it got infected. Each speaker that came after her felt that he needed to show their river, from whatever country or state they're from. So I really liked what Aviv did later, because he showed I thought it was one of the most awful headlines for a talk, I thought, and then you simplified it. So maybe we can start a trend changing headlines that only make sense to the one person that speaks. And I would change mine to dendrimers or dendrons are great. So maybe you can take it or leave it. I don't care. I care. And I think my first slide depicts that the self-assembly of an amphiphilic block of polymer in water can form polymeric micelles that can encapsulate small hydrophobic drugs. I think Peter showed before, he touched a couple of neat examples of amphiphilic structures that form nanostructures in water. And I think Ronit gave an excellent talk that showed nanocarriers that can carry drugs or dyes. Obviously, the advantages of such a carrier is the increased solubility in water that the guest gets, and we get increased circulation in the bloodstream, and we also get a protection from the immune system. It gives the guest stealth properties. So I wrote controlled delivery with a question mark because in the 15, 20 years, the past 15 or 20 years, people have been working very hard to design triggers that can cause the nanocarrier to disassemble and release its cargo. And people have been focusing mostly on pH, light, and temperature as potential triggers. And in our group, we do two things differently. First of all, and not surprisingly, instead of a linear hydrophobic segment, we use a dendron, which its terminal ends are functionalized with hydrophobic end groups. And we design our polymeric micelles to disassemble in response to an enzyme. The reason why we think enzymes are great, have great potential as trigger is their high specificity towards their substrate, they're catalytic, and they're already present in the biological tissue. As Ronit said in her talk, we can see a coloring of a cathepsin B enzyme in this breast cancer cell. And if we could program our nano containers, vehicles, to disassemble specifically in these areas, we could induce a smart delivery platform. So our molecular design includes polyethylene glycol, or PEG, as the hydrophilic polymer. And to the active end of the PEG, we grow a symmetrical and hydrophobic dendron unit. So our initial model included phenylacetamide as our end groups, which cause the structure to be amphiphilic and hence can form micelles in water. Now, the enzyme penicillin G amidase, or PGA for short, knows how to recognize these amides and hydrolyze the amide bond. This results in leaving amino-protonated groups in the end of the dendron, and causes the structure to become hydrophilic, which makes it still soluble but not assembled. So this is our strategy in order to cause the micelles to disassemble in response to the enzymatic activation. So I don't know how many chemists are there in the audience, but our buildup of the hybrid is very simple. If we take a 5 kilodalton amino PEG, which we make in 2 steps in gram scales, we connect something in the first step we call a branching unit, which is just a benzoic acid with 2 triple bonds. The reason why we put triple bonds is because we like to use thioline click chemistry between this commercially available thiol and the triple bond. For those who doesn't know, in thioline chemistry, each one of the carbons of the triple bond gets clicked to a thiol, and this gives us an accelerated growth of 4 protected amino groups. So in the last step, the functionalization step, we remove the protection groups from the amines, and we functionalize the dendron ends with whatever groups we want. So in the model, in our case, we simply put phenylacetic acid, which makes phenylacetamide in the ends. So I'm not sure if it's all right to put an NMR spectrum in convention, but I'm sure that if I will remind you that this is a 6.1 kilodalton hybrid, and this is the PEG in the middle, we can pretty much see even the splittings. And this is 400 megahertz NMR, not 800 or 700. We can even see splittings of triplets of a single hydrogen. So I've shown you how we can get a hybrid with 4 N groups from this branching. And in this project, we were interested to discover whether the number of N groups can affect the disassembly rate of the formed micelles. So first of all, we wanted to decrease the number of N groups from 4 to 3. This has no, oh, it's okay. And in order to do so, we had to change was the branching unit from 2 triple bonds to 3 double bonds, and then do the same process, the 3 steps. In order to increase the number of N groups from 4 to 6, all we had to do is to change the branching unit again and put another triple bond in the middle and get 6 N groups. And then like a typical male, I thought, well, why 1 when we can have 2? So instead of a mono amino PEG, I used diamino PEG and did the same thing again. And instead of 1 dendron units, I can have 2. And so we obtained a series of 6 hybrid. All of them have a 5 kilodalton PEG. And the number of N groups varies from 3, 4, 6, another kind of 6, 8, and 12 N groups. Hopefully, it's under revisions, and next week it will be published, this work. So the first thing we do when we get our hybrids is to measure the critical micellar concentration, or CMC. So we use a Nile red as our fluorescence marker, and it has the following property. In the presence of hydrophobic cores, the emission intensity is high. And in water, or in the absence of micelle, the emission intensity is low. So we use a different concentration of hybrid, moving from 500 to 0.1 micromolars of the hybrid. And it's important to emphasize that the concentration of Nile red is constant. It doesn't change, but the emission intensity changes. So when we plot the maxima of the Nile red as a function of the concentration of the hybrid, we can see that at low concentrations we have low emission intensity. And at a certain concentration there is a spike of intensity, and that cross-section of these 2 trends can help us to measure the critical micellar concentration of the hybrid. So we can see that when we added, this is for the 3 N groups hybrid, when we added 4 and 6 N groups, the critical micellar concentration decreased because the hydrophobicity of the dendron unit increased. And we decreased from about 50 micromolars to about 10. When we added another dendron, the hydrophobicity also increased, and we lowered the CMC to about 5 or 3 micromolars. Another characterization we do is measuring the size of the micellar aggregates by DLS. And we can see that for all of the 6 hybrid, the micellar size range from 20 to 30 nanometers. And hopefully I've convinced you that we can make this part, to characterize this part, the self-assembly part, but I haven't told you anything if the enzyme is capable of causing the micelles to disassemble. So the first thing, we use again Nile red fluorescence in order to detect disassembly of micelles. So we mix the Nile red with the micelles, we measure the fluorescence at T0, we add the enzyme and we monitor the fluorescence over time, and we see that it decreases. So again, we can take the maximum of the fluorescence, plot it as a function of time, taking this change of fluorescence, plot it as a function of time, and we can say that at this part we had micelles, and in this part, most of the micelles disassemble because the change in fluorescence decreased. So, and then we thought to ourselves, okay, the fluorescence told us whether micelles are present or don't, or ain't. And we said, okay, we have a symmetrical dendron unit. Does the enzyme cleave the 4 N groups from here to here in a single maneuver, or it has 3 intermediates where one group is cleaved and then another one, a third one, and then you get the fully cleaved hybrid. So what we did in order to see what happens is we took the hybrid against my supervisor's will, and I injected it to the HPLC. And I got this amazing picture, okay? At T0, I'm seeing my hybrid at 1 peak, and then I'm adding the enzyme, and I can monitor the disappearance of the peak area. But the fully cleaved hybrid, which I had in my disposal synthetically, I saw that I'm not reaching it. I will help you visually, 1, 2, and 3 intermediates. And I can really integrate the areas and put it on a plot. So this is the degradation of the first hybrid, and then the enzyme cuts one group, so it forms, and then it consumes to form a second cleavage and a third cleavage, which we can see the enzymatic activation becomes slower in time. And then I ask myself, or you should ask yourself, but what about the micelles? Because unfortunately, HPLC does not tell you if you have micelles in the solution or you don't have micelles in the solution. But when you use Nile red fluorescence under the same condition and plot it on this graph, and let me take away the green and the purple lines for your eyes' convenience, we can see that an excellent correlation between the degradation of the hybrid and the decrease in the fluorescence of Nile red. So we could conclude by using dendrons, which are great, that it only took one enzymatic cleavage to cause most of the micelles to disassemble. The enzyme did not need to cleave all the groups, it only had to cleave one. So now back to our series of hybrids, we wanted to compare them. So we took the least 4 hydrophobic, the 3, 4, and 2 6s, and I started to degrade them in the HPLC. and to compare the rates. So when I took the hybrid which has the two hybrids that has 3 and 4 N groups, I got what you say, I think also in English, not something to write home about. Okay, because this difference is very almost non-existing. But when the number of N groups increased to 6, suddenly there was a jump in the stability of the formed micelles towards the enzyme. When the 6 N groups were dispersed over 2 dendrons, the stability increased. So we could easily play between very sensitive polymeric micelles and very stable polymeric micelles with very simply. So this is the HPLC monitoring of the parent hybrid. The same experiment using fluorescence of Nile red shows a correlation between the decrease in the parent hybrid and the fluorescence of Nile red. And in order to double check that the micelles were disassembled, after 4 hours, the 3 and 4 N groups, the peak of the micelles disappeared. And after 24 hours, at this point, the micelles of 6 and 3 plus 3 did not disappear because there was substantial amounts of parent hybrid to form micelles. So I simply took the most hydrophobic hybrids and did the same experiment using an increased amount of enzyme because I wanted to cause them to disassemble and not wait 2 weeks for it. So we can see that using an increased amount of enzyme, the 2 6s disassemble, also the 8, but when I put the 12 N groups, the enzymatic activation stopped. The micelles were too stable to be degraded under these conditions. We can see that the fluorescence of Nile red under the same condition correlate very nicely, and we can double check the presence or disassembly of the micelles using DLS. We can see that the 12 N groups does not disassemble. So to conclude my talk, some take-home messages. Very small chemical modifications to the hydrophobic block, the responsive block of your polymers, may have very large effects on the assembled state. Okay? So using dendrons is a very smart way to control it and to test it because dendrons are very structurally characterized. And I would like to end with a small, Einstein said, a thought experiment. I want you to think and compare the dendritic version of 8 N groups and the linear version of 8 N groups. So when the hydrophobic segment orients from a polymerization, we get a statistical number of N groups where, okay, the average is 8, but you also have 7 and 9s. You also have 6s and 10s. So when a lot of papers show a drug release over time, and you see only partial release or partial degradation, you must ask yourself, what is the cause of this effect? Was it that all of the molecules degraded 50%, or that the ones that carry the lower number of hydrophobic groups were disassembled, and the ones that carry the higher number formed very stable assemblies that could not be degraded? So with that, I would like to thank my PI, Roey, my group, our collaborators, funders, and of course, you for your attention. You can see me at board 16 for more questions.
Any other questions? So, for the bravery, students presenting.
Thank you.
Let's thank the students.